My other main headline, which is that there's many things in the system where we built really general infrastructure, very general data types that are super, super flexible. That if you think back to the list language construct that we've had since version 1, that always been very flexible. You've been able to make a list of anything. You can have a list of numbers or strings, but it could also be a list of documents or images or sounds, and all of these things are very flexible. The downside of that is that there are often things you can do either more elegantly, more automatically, or more efficiently if you are working in a narrower domain where you can anticipate structures that are more appropriate. It's sort of a performance versus flexibility kind of trade-off. So one of those big areas has been working with tabular data, where we've had no trouble working with tabular data for a long time. It's a relatively simple structure, but the tools that we built, all the various sort of linear algebra tools, are very focused on tabular data, which is numbers. The data set kind of infrastructure works with tabular data, but it doesn't assume tabular data, and so it has to do things slightly more complicatedly because it has to worry about whether things are, mixtures of high depth hierarchical data sets and the kinds of very clever things it can do. But tabular data is a really common area of data science. So we're talking about rows and columns that form a grid, the kind of thing that you would do in Excel. And in fact, Excel enforces on you because its only world is tabular. And one of the characteristics of tabular data tends to be that the columns are quite homogeneous, that you will have a column of dates or a column of numbers or a column of labels, and the rows tend to be kind of fairly independent. They're observations. So that's the kind of narrower field that we've now looked at and said, okay, if we wanted to handle that kind of data, how could we do that better? Because it is a big fraction of data science. SQL data always comes out in tables. Spreadsheets and things like CSV files are all basically tabular data. So it's really common. So I'm going to go through here a sort of simplified data science workflow where I'm going to get some data in, import it into the system, clean it and canonicalize it, and then do some computation on it. And it turns out that the framework that we've built is got really important things to say at each stage of this. So first of all, getting it in. There's some well-established formats that are very common in this space, like Excel files, like CSV, or the open spreadsheet format, TSV, table formats, and so on. So if we're really focusing on this area, one of the things we want to do is speed that up. I mean, I'm just going to import some data here from a tabular, and it's taken 2.5 seconds to bring in 1.5 million rows of data. So I haven't timed it on this. I'm on a Windows machine that's a little bit puny compared to my 2-year-old Mac laptop, but on my Mac, I time that to be about 5 times faster without having to do anything special. Just CSV is a popular format. We've given it some attention and accelerated that by a factor of about 5. In fact, in a minute, you'll see that we're doing even more than we were in that reduced time. So it's not just that it's less time, it's doing more in less time. Those are ancient formats. CSV goes back probably before I was born, or certainly somewhere around there. But there are more modern formats that are focused on this kind of column-oriented data. So Parquet being one of those. And so we've added support for Parquet, Awk, Arrow RPC, and Arrow Dataset. And if you start using these more modern data sets, then the same file, the same 1.5 million rows of taxi cab data from New York has now imported about, 5 times faster than the 5 times faster. So that if we can get it in Parquet format in the first place, then we can get it into the system about 25 times faster than previously. And of course, it doesn't really matter that much for something that was previously going to take 15 seconds. It's not a huge deal, but 1.5 million rows isn't that big a data set. So when you start getting to big data sets, then it starts becoming the difference between practical and impractical when those sort of import times start creeping over multiple minutes just to even get started. And now we can do that in seconds. That's a big improvement in practicality. Now, another part of this is that we want to be able to do better with big data. So data that is not even kind of in the few million or tens of millions of rows, the kind of things that you can hold in memory. We want to be able to deal with data that is larger than you can hold in memory. And there's a new mechanism that is seamlessly integrated in with that of being able to declare that I've got some tabular data, but I'm not actually going to import it. I'm just going to point to, in this case, an SQLite database and a particular table within that. And I get an object now that allows me to do all the operations you'll see in a minute, but it doesn't actually do them immediately. It treats them as symbolic operations. So if I ask for something like a selection of the rows in that data set which have country equals USA, I can do that without ever having brought the data into memory. Effectively, what it's doing is a certain amount of symbolic representation and simplification on something that is really an inert object. At some point, we need a concrete result, and at which point I can say to memory, and then it will effectively execute that. And I get my 3 rows without the previous way we would have had to have done that is either resort to low-level SQL, and you're having to kind of write code to access the right data, or you would bring the whole data into memory and then throw away most of it in order to shrink the memory footprint back down again. And now we can do these kind of start building up code and operations without ever having to touch the masses of data. We only end up having to bring into memory the bits that survive the filtering and transformations and whatever it is that we're doing along the way to that data. Relatively small, but also a nice bit of convenience is there is a new symbolic representation of data stored in distributed and remote file systems. Basically, it's a package of credentials. So you can set up a data connection object that has the information it needs to be able to reach into the Amazon S3 bucket or Azure blob storage and fetch out information. It's basically a form of import, but it's a way of brokering all of those handshakes and crypto signature type things that protect the data to make it a reference that you can pass around within code to access remote files in these big storage systems. So the headline thing really here is faster import, but actually it's also about scalability, that we're trying to get into this out of core computation space and large storage systems for remote data. Now, what's the thing we actually got in there? You saw sort of passing reference to Tabular. The data that I've imported from that Parquet file, it's a new object within the Wolfram language, and it's an object that basically declares that its contents is tabular data and brings, by virtue of that wrapper, a certain amount of automation. So one of those bits of automation is that it formats very prettily. So here is the output of that tabular data, and in the notebook, it will render as one of these table view objects where, even though we've got 1.5 million rows, I don't have to pollute the entire notebook with lots of data here. This data is being sort of fetched on demand as I browse through it, and I have a kind of nice view on what's there without having to have a huge notebook. If we mouse over the top here, and I don't know if that's probably very small font on your screen, so I'll read it to you. It's a little tooltip appeared there, said pick update time. That's the name of the field, which you could see already. Brackets date. So one of the things that we're bringing to bear here is that this table has a notion of typing within it, and this is where some of the performance magic is going to come from. And I can ask it actually in a much more formal way, what is the structure of this data? And you can see here that I've got first column is called ID, and it's a string, and there's 1.5 million records in there, and it's taking a certain amount of memory. But we have some very compiler-friendly types going on here, that this column is real 64s, and 2 of these columns are dates. And this is what I meant by it's doing more than just the import. That in that 5 times faster, it's actually parsed all of those date strings that previously when you imported from CSV and you had dates, you would get a column of strings, and then you would have to map date object down the strings to interpreter down that column in order to canonicalize it. And that's happened at import. It's recognized those are dates, and those are now dates within the system ready to do date difference or date plus or whatever kind of or selection I want to do on them. Now, one of the things that being able to rely on homogeneous types, and there is a general type, there is a expression type for things where you've got a column that is just a mix of numbers and dates and other things. But where it is quite structured data, that allows us to bring all this compiler technology that we've been using to do type accelerated computation. So as an example of this, I'm going to escape the tabular object. Normal will turn any tabular back into a regular list of associations that Wolfram language has been able to do for years and years. So it's totally compatible with the code that you have if you need to step in or out of the tabular object, although there's a cost each time you go each way, so you don't want to flip backwards and forwards unnecessarily. But if I just take that column of dates, which did I take? I took the pickup date time. So there's 1.5 million dates, and I am asking a simple question using the old data structure of what is the biggest date, the most recent date within that column. Now, because of the generality of lists and associations, it has to think about every one of those records and say, what is this? Oh, it's a date. I know how to compare dates. What's this? Oh, it's a date. I know how to compare dates. And so, not terrible for 1.5 million date calculations to rank them and find the most recent. But by virtue of this compiler accelerated column type, if I stay within the tabular, I don't need to keep asking that question, is it a date? It knows the column's a date, and it can use a kind of compiled version of Max that knows how to deal with those date objects. And that 25-second operation is now, I can't even put that into words, that's tenths, hundreds, thousands, 8/10,000ths of a second. So about a 10,000th of a second, about a thousandth of a second to do what previously took 25 seconds. Now, dates are a big win, but this is generally true that now, by virtue of having this optimized data structure for tabular data, assuming your data is suitable for that, we can really optimize operations that are being performed on the data set and do, again, things that were maybe doable at small scale but became unfeasible for large data, and now fast enough that they become feasible for even really very big data sets. Right, so we've got the data in. We've got this great representation that's going to be really efficient. There's various things to say on cleaning, some of them kind of fairly prosaic, but in the end, they're important to be able to do elegantly and efficiently. So things like transforming the contents of columns. And we have some utility functions here that are designed to efficiently and in single pass transform lots of records, lots of columns within each record. So what I'm saying here is take those 1.5 million rows of data, and I'm going to take the store and forward flag, and I'm going to compare it to the letter n, because whoever provided this data has used y and n to decide true or false. And I'd rather have this in a canonical Wolfram language, true or false. And there was a pickup latitude and a pickup longitude. So I want to add a new column here called pickup location, which is going to be a combination of those two columns combined into this new column. And we can give as many rules as we want in this transformation. And in a single pass of the data set, we get a new data set, new tabular out, where if I scroll through this thing, you'll see somewhere here there is our store and forward is now trues and falses. It replaced that column, but our pickup location is a new column that is now a geo position in a nice Wolfram language geo position object, and it probably has some type here in inert expression. Okay, that one isn't optimized. Similarly, we can throw away columns we don't want. Again, in a single pass, I can just say pick off certain columns that we want to get rid of, and they're all gone. We can rename columns, so I could give them more Wolfram language style phrases. And so fairly quickly here, I've cleaned this up into canonical types, owning columns I want, and we've only had to pass through the data set 3 times, once for the transformation, once for the rename, and once for the column drop. And some of those can actually, with a bit of coercion, be made to do in a single pass. Now, one big part of the whole kind of cleaning process is anomaly handling. That and things that aren't meant to be there, or values that are out of range, are things that we kind of want to deal with, but we also don't want them to break our beautiful column homogeneity. And so the tabular framework deals with that as well. In my taxi cab data, I'm going to make an almost certainly false assumption here that no taxi journey can be more than 2,000 seconds. So I'm going to replace any durations above 2,000 with missing in the data set. So even though this column was of type, I think it was type real, real 64, it might have been integer 64 in the original, I want to insert some missings into that. And I'm using the transform columns that I showed a moment ago. So we're just replacing the duration column with a modified version of duration. And you can see here now, down here is a missing item where it was out of bounds, and we've decided that it's missing. But the type here is still integer 64 on this tooltip. And that's because if we look at the tabular structure, we're treating missings as a special case because they come up so often. We've got a column which is integer 64. It's got 1.3 million non-missing values and 84,000 missings, but those don't change this and force it into some kind of expression type representation that is really general. So we've sacrificed nothing by putting missings in. Now, missings, it's all kind of easy to put them in. It's dealing with them can sometimes be problematic. And a little digression here. This is a typical problem that anyone who writes Wolfram language code ends up having to write fairly trivial but annoying code to get around. I got some data and I want to do something like map a function over that data. And map is nice and elegant, says take the square root of every element of example. But the trouble is square root of missing isn't defined and square root of $failed isn't defined. And so we end up having to make special cases of saying, well, if it's a number, then take the square root, otherwise do something else. And we now just have a really elegant little utility function that we can wrap around any operator or functional expression and map a fail-safe version of square root over that list. And now things like missings and fails gets passed through whatever the operation is I'm trying to do, and the operation is only applied to the places where it's not missing or not failed or other kind of pathological things like $cancelled that might be in there. So it's just a utility function, but I think these little things in Wolfram language that help you to write really readable and compact but robust code are really kind of useful. And I'm going to use it right here by saying, okay, I'm going to transform that duration column from integers into Wolfram language quantities. So I'm doing a kind of type transformation on the column by saying I want the quantity of that number in seconds is what that column means. A bit more canonicalization. Now, this is going to coerce the whole column type. And when we finish here, we'll see hopefully the data set. Duration, you can now see type here. It says duration quantity integer 64 seconds. So the type information is now attached. The column itself still has in it, its display is still just to show the number, but every time I pick numbers out of this, these will now be quantities. So if I did that convert to minutes, it will now just work. But the missing has not ended up as missing of quantity of missing, it's just missing. So it still will be handled seamlessly in all future operations. Now, the question is, what do you do with missings? And there's lots of strategies depending on the context. And we've got this new fairly useful general function for dealing with missings. In the past, the only functionality we provided was delete missing. So you could delete the missings out, or you could delete rows that had a missing, or rows that had a missing somewhere deep within them. But now we have this sort of super function with all kinds of methods to be able to take that data set. And in this case, I'm imagining that the reasonable thing is to say these are sequential. So maybe the best estimate for this duration is some interpolation between the estimate before, the time before, and the time after. That the best guess for filling in this with some actual number would be somewhere in the 500 range. And so that's what this transform missing interpolation does. There's lots of sub options, as you might expect, like the interpolation order and so on. And now you can see that in my new data set, I can't remember, there was 100,000 missings in the data set. They've all now been filled in with an interpolation of their before and after. Actually, I happen to know these taxi journeys are independent observations, so interpolation is probably a bad idea. So maybe I want to do something like a random element or a fixed value, or a random number from a given distribution. There's lots of ways that I could make synthetic data to fill in the gaps. And they're all wrapped up in this transform missing function. If you look at the documentation, you'll find about a dozen methods in there. We got the data in nice and fast. We got cleanup nice and fast. We're handling missings in a better way than before. In the end, you're doing this for a reason. You want to compute something, and there are all kinds of ways of doing direct operations on the data set. We can do things like select and apply functions, all the kinds of things you would do with data set in the past in a fairly direct way. But in the world of tabular data, there are certain kind of operations now become in more general data structures are kind of pointless, because you can't. There's so many cases they don't work. They become just silly functions. So one of those is aggregation. So I can take my data set here. I'm sorting it first, but then I'm going to say I want to find the mean trip time. So I'm giving that a name. It's not a column that's in my data, and that's going to be the mean of the durations. But I don't want to do that for the whole column. I want to do that per vendor ID. So we've split the data into sets of each vendor ID, and then within that set, we've aggregated all of the records down into a single number. So you could have done that before. You would probably have to write 2 or 3 lines of code, and you might even have to think a little bit about how to deal with how the aggregating function deals with what's in there. That's now this kind of neat aggregate rows function. And the one thing that my business department Excel jockey colleagues have always made me jealous of is pivot tables, which there's a nice little button to make a pivot table in Excel, and you have to write a fairly cryptic 2 or 3 lines in dataset. There is now a pivot table function that allows me to say, what are the rows and columns? So again, we're splitting the data by 2 dimensions now. And then within that combination, so the 0 passenger journeys for vendor ID number 1, find in this case the average. And that's the average time for vendor 1 on passenger 0. I've got a useful little option here to throw an all column on the bottom and right hand side. And so now we've stratified the data in 2 different dimensions, and we can see fairly at a glance the comparison between vendor 1 and vendor 2 in this New York taxi cab data, that vendor 2 tends to be the only one that takes large loads of passengers, so they're the only ones with the minibuses, and vendor 1 seems to be doing generally longer journeys for the smaller passenger set. And we can see the set-by-set weighting. But unlike Excel, of course, we can scale this to very large data, and the kinds of aggregation we do can be any Wolfram language function. So while mean and total are the kind of 2 obvious ones, and max and min, I guess, also pretty obvious, there's any number of kind of ways you can do of collecting a bunch of records together and making a thing that you want to see that represents that you want to do sliced over each of the 2 conditioning parameters. Also, a lot of the standard functionality has been extended just to recognize what to do with tabulars. So let's get in another tabular data set here, just because it's more amenable to machine learning. I've got a tabular of flour measurements. Well, classify knows how to deal with tabular objects, so I can just say classify that tabular object where I'm trying to pick the species from everything else. So you don't have to start doing drop column species, generate a training set from the remainder, build the classifier, and then figure out how to take a random sample from that and pass it back into the classifier. We can just sample that tabular. We can apply our classifier function to the rows of that new sample tabular to get our 3 predictions out. The visualizations all kind of know about tabular, so I can, again, without having to slice out a column and then plot it, I can simply say, I want a histogram of that data but I'm only interested in the passengers column. And this sort of neat selection syntax also applies to multivariate things. So I could plot, for example, the pickup time versus the duration for the first 200 rows in that tabular. Particularly things like visualization commands all kind of recognize automatically how to deal with tabular objects and have a neat syntax on top.